The second law of thermodynamics. This topic introduces the second law of thermodynamics as the law that determines the natural direction of all energy processes. Unlike the first law, which only discusses energy conservation, the second law deals with energy quality and direction. Not all heat energy can be fully converted into work. This law explains why there is an efficiency limit in heat engines. This concept becomes the foundation for understanding heat engines, refrigerators, and heat pumps.
Lesson Plan Thermodynamics 1. The course structure is arranged progressively from basic concepts to advanced applications. This chapter comes after the discussion of mass and energy analysis for closed and open systems. This means students already have the foundation of energy analysis before learning the second law. The second law completes the analysis by adding direction and efficiency limits. With this flow, the understanding becomes more systematic and continuous. Learning Outcome. The learning outcomes show that the main focus is not only understanding definitions, but also being able to apply them to cycles and thermal machines. Students are expected to distinguish physically possible and impossible processes. The concepts of reservoirs, heat engines, refrigerators, and heat pumps are central topics. The Carnot Cycle is introduced as the ideal performance limit. All of these lead to quantitative understanding of efficiency and COP. Heat transfer concepts. The example of hot coffee cooling down shows the natural direction of heat transfer. Heat always flows from high temperature to low temperature without external work. This process continues until thermal equilibrium is reached. This simple phenomenon is a direct manifestation of the second law of thermodynamics. From here, it becomes clear that the direction of thermal processes cannot be spontaneously reversed. Heat and electricity. Heating a conductor alone will not produce electric current without an additional mechanism. This shows that heat cannot be directly converted into electrical work in a simple way. A special system, such as a thermoelectric device or heat engine, is required. The second law limits the possible forms of energy conversion. Thermal energy always needs a system to produce useful work. Check your understanding. Number 1. This question emphasizes that heat alone is not enough to produce electrical effects. There must be an external source that provides a conversion mechanism. This reinforces the idea that the second law limits what heat energy can and cannot do. Without a conversion system, heat will only flow and be wasted. This concept is important before moving to heat engine discussions. Heat and mechanical motion. Heat supplied to a system, like a paddle wheel, does not automatically produce motion. An organized mechanism is needed to convert thermal energy into mechanical work. This shows that conversion from heat to work is never direct and always limited. The second law states that not all heat can become work. There is always some energy that must be rejected. Irreversibility in processes. Many processes in nature occur only in one direction. These processes are called irreversible because they cannot return to the initial state without leaving changes in the surroundings. Friction, heat transfer, and mixing are common examples. All these processes are associated with an increase in entropy. This is the fundamental reason why time has a direction in thermodynamics. Thermodynamic process laws. A process is not sufficient if it only satisfies the first law. Besides energy conservation, the process must also satisfy the second law regarding direction and physical feasibility. There are many processes that are energetically possible, but thermodynamically impossible. Therefore, both laws must always be used together. This is the main filter to judge whether a process can occur or not. Thermal energy reservoirs. A thermal energy reservoir is a large body whose temperature practically does not change when absorbing or rejecting heat. Examples include oceans, lakes, or the atmosphere. In analysis, reservoirs are treated as ideal heat sources or sinks. This simplification greatly helps in modeling heat engines and refrigerators. With this concept, system analysis becomes much more structured. Thermal energy flow. Thermal energy flow always occurs from a heat source to a heat sink. This direction is determined by temperature difference and never occurs spontaneously in the opposite way. The concepts of source and sink are essential to understand heat engines and cooling systems. All thermal systems operate by transferring heat from one temperature level to another. The second law ensures that this direction always has a natural constraint.
Answer C. Heat transfers from sources to sinks following temperature gradients. Explanation. A. Heat transfers from sinks to sources following temperature gradients. This is incorrect because heat always flows from areas of higher temperature, sources, to areas of lower temperature, sinks, not the other way around. B. Thermal sources absorb heat energy from surrounding systems. This is incorrect because thermal sources supply heat energy. They do not absorb it. C. Heat transfers from sources to sinks following temperature gradients. This is the correct answer. Heat always flows from higher temperature areas, sources, to lower temperature areas, sinks, as part of the natural thermodynamic process. D. Thermal sinks supply heat energy to systems and surroundings. This is incorrect because thermal sinks absorb heat, not supply it. Work and heat conversion. Mechanical work can be fully converted into heat, such as in friction or braking. However, heat can never be fully converted into work. There is always some heat that must be rejected to the surroundings. This is the core limitation imposed by the second law on heat engines. That is why 100% efficiency is physically impossible. Heat engine process. A heat engine works by absorbing heat from a high-temperature reservoir. Part of this heat is then converted into useful work. The remaining heat that cannot be converted must be rejected to a low-temperature reservoir. This process is always in the form of a cycle, so the engine can operate continuously. This structure clearly shows the limitation imposed by the second law. Steam power plant cycle. A steam power plant is a real example of heat engine application. Heat from an energy source is used to produce high-pressure steam in the boiler. This steam then drives a turbine to produce work. After that, the steam is condensed and its heat is rejected to the surroundings. This cycle repeats continuously as long as the plant operates. Heat engine work. Not all the work produced by an engine can be used as net output. Part of the work must be reused to operate internal components of the system. Only the remaining part becomes the net output to the outside. This shows that even at the system level, there are always internal needs that reduce the net output. This concept is important when calculating real engine performance. Check your understanding. Number 3. This question emphasizes that part of the work is always used to maintain system operation. An engine cannot operate without sacrificing part of its own output. This is a characteristic of all real cyclic systems. This concept helps distinguish between total work and net work. Without this understanding, efficiency analysis can become misleading. Heat engine efficiency. Not all heat engines have the same efficiency. A more efficient engine can produce more work from the same amount of heat input. A less efficient engine will reject more heat to the cold reservoir. Efficiency becomes a measure of the quality of energy conversion in a system. This concept is very important in the design and evaluation of power plants.
Heat engine schematic. A schematic diagram helps visualize energy flow in a heat engine. Heat enters from the hot reservoir. Part becomes work, and the rest is rejected to the cold reservoir. This representation is general and applies to all types of heat engines. With this diagram, energy balance becomes easier to understand. It is a very powerful conceptual model in thermodynamics. Heat engine efficiency. Heat engines always reject a significant portion of their energy as waste heat. Even very good engines are still far from 100% efficiency. This limitation is not due to technology, but due to the laws of physics. The second law sets a maximum limit that cannot be exceeded. This is why improving efficiency is always a major challenge in energy engineering. Heat engine cycle. A heat engine cycle describes a repeating process that allows continuous production of work. Heat is absorbed from a high-temperature reservoir to drive the system. Part of this energy is converted into useful work. The remaining heat must be rejected to a low-temperature reservoir. Without this heat rejection process, the cycle cannot be completed. Second law violation. An engine that claims to convert all heat into work without rejecting any heat is an impossible machine. Such a claim directly violates the Kelvin-Planck statement of the second law. No heat engine can operate without a cold reservoir. The existence of a cold reservoir is a physical necessity, not a design choice. This shows that 100% efficiency can never be achieved.
Answer B. It violates the Kelvin-Planck statement of thermodynamics, which states that no engine can be 100% efficient. Explanation. A. It can exist if all input heat is converted to work without rejecting heat to a sink. This is incorrect because a 100% efficient heat engine would violate the second law of thermodynamics, specifically the Kelvin-Planck statement, which asserts that some heat must always be rejected to a sink. B. It violates the Kelvin-Planck statement of thermodynamics, which states that no engine can be 100% efficient. This is the correct answer because the second law of thermodynamics prohibits a heat engine from being 100% efficient, as it would require no heat rejection, which is impossible. C. It is possible as long as the engine operates at absolute zero temperature. This is incorrect because even at absolute zero, the second law of thermodynamics still applies, and an engine cannot be 100% efficient. D. The engine would not violate thermodynamic principles if it were designed with zero entropy. This is incorrect because entropy is inherent in all processes, and a zero entropy engine would still violate the second law, which requires entropy generation. Refrigeration cycle. A refrigeration cycle works by absorbing heat from a cold space. This process requires external work supplied through a compressor. The absorbed heat is then rejected to a warmer environment. In this way, the temperature of the cold space can be maintained. This is the reverse of how a heat engine operates. Refrigerator function. The main function of a refrigerator is to move heat from a cold place to a warmer place. This process clearly goes against the natural direction of heat transfer. Therefore, external work input is required. The performance of a refrigerator is not measured by efficiency, but by the coefficient of performance. The more heat removed for the same work input, the better its performance. Heat pump function. A heat pump has the main purpose of heating a space, not cooling it. This system transfers heat from a cold environment to the space that needs heating. External work is still required to move this heat. Its advantage is that the heat delivered can be greater than the work input. This makes heat pumps very efficient for heating applications. Heat pump efficiency. The efficiency of a heat pump is expressed using the coefficient of performance, or COP. A high COP value means the system is very effective in using the supplied work. This is possible because the system does not create heat, but moves it. The smaller the temperature difference, the higher the COP is usually. This is why heat pumps are very attractive from an energy perspective.
Check your understanding. Number 5. This question emphasizes that the performance of a heat pump is not measured by ordinary efficiency. The key term that must be understood is COP. This concept is different from heat engine efficiency. Many students often confuse these two concepts. Understanding the difference is very important for analyzing cooling and heating systems.
Clausius statement violation. If there were a system that transfers heat from cold to hot without work, it would violate the Clausius statement. Such a process never occurs in nature. This is a fundamental limitation of the second law. All refrigerators and heat pumps always require work input. Without work, such heat transfer is impossible.
Kelvin-Planck and Clausius connection. The two statements of the second law are actually interconnected and equivalent. If one is violated, the other is automatically violated as well. A perfect heat engine could be used to drive a refrigerator without work, which is impossible. This relationship shows the internal consistency of the second law. No matter the perspective, the conclusion is always the same. There are physical limits that cannot be violated. Kelvin-Planck and Clausius connection. The relationship between the Kelvin-Planck and Clausius statements shows that they express the same physical law from different perspectives. If a heat engine had 100% efficiency, its work could be used to transfer heat without additional work. This condition directly violates the Clausius statement. Conversely, if Clausius is violated, then Kelvin-Planck is also automatically violated. This proves that both statements are physically equivalent. Perpetual motion machine, PMM1. A perpetual motion machine of the first kind claims to produce energy without any energy input. This claim directly violates the first law of thermodynamics about energy conservation. Such a system appears to create energy out of nothing. In an energy balance, its output is always greater than its input. Therefore, PMM1 is physically impossible. Perpetual motion machine, PMM2. A perpetual motion machine of the second kind claims to convert all heat into work. Such a machine does not reject any heat to a cold reservoir. This claim violates the second law of thermodynamics. Even though it does not violate the first law, it is still physically impossible. This shows that the second law provides additional restrictions beyond energy conservation. Answer A. It violates the second law of thermodynamics by assuming perfect conversion without any losses. Explanation. A. It violates the second law of thermodynamics by assuming perfect conversion without any losses. This is the correct answer. The second law of thermodynamics states that it is impossible to have 100% efficiency in a heat engine because some energy must be lost as heat to the surroundings. B. It is possible in real systems due to advanced technology overcoming thermodynamic limits. This is incorrect because even with advanced technology, the second law of thermodynamics cannot be violated, and 100% efficiency is not achievable. C. It operates without needing to expel heat to a sink, which is allowed by entropy principles. This is incorrect because according to the second law of thermodynamics, some heat must be rejected to a sink to avoid violating entropy principles. D. It achieves perfect efficiency by eliminating all irreversibilities in the system. This is incorrect because it is impossible to eliminate all irreversibilities in a real system, and perfect efficiency cannot be achieved. Reversible processes. A reversible process is an ideal process that can be reversed without leaving any change in the system and surroundings. Examples include a frictionless pendulum and quasi-equilibrium gas expansion. In reality, such processes never truly exist. However, this concept is very important as an ideal reference. All real machines always deviate from reversible conditions.
Reversible versus irreversible. Reversible processes occur very slowly and uniformly so that no imbalance is created. Irreversible processes occur rapidly and involve pressure or temperature gradients. As a result, there is always energy dissipation and entropy generation. Reversible processes produce maximum work for the same conditions. That is why reversible processes are used as a reference standard.
Effect of friction on processes. Friction is one of the main sources of irreversibility in mechanical systems. Work that should be useful is converted into heat that cannot be utilized. As a result, system efficiency decreases. Friction also increases the total entropy of the system and surroundings. This shows why real systems are always worse than ideal ones. Irreversible compression expansion. Very fast compression or expansion creates pressure non-uniformities. The flow becomes turbulent and a lot of energy is dissipated. Free expansion is an extreme example of an irreversible process. In all these cases, part of the work potential is lost forever. Such processes can never be perfectly reversed. Heat transfer processes. Heat transfer from hot to cold is always an irreversible process. It is impossible for heat to flow from cold to hot without external work. This direction is a direct consequence of the second law. Every heat transfer with a temperature difference always generates entropy. That is why this process cannot be simply reversed. Check your understanding number 7. This question reinforces that transferring heat from cold to hot requires external work. This is the basic principle of all refrigerators and heat pumps. Without work, such a process violates the second law. This concept is very important and often appears in exams. If this is understood, many conceptual confusions will disappear. Reversible process characteristics. A reversible process requires the absence of friction, turbulence, or unbalanced forces inside the system. Heat transfer must occur with an infinitesimal temperature difference. All of this is intended to prevent entropy generation. Such conditions can only be approached but never truly achieved in the real world. However, this concept is very important as an ideal reference. Reversible heat transfer. Truly reversible heat transfer is only possible if the temperature difference approaches zero. If the temperature difference is large, the process is definitely irreversible. Internally reversible means there is no source of irreversibilities inside the system. However, externally, there may still be irreversibilities. Total reversibility requires conditions that are almost impossible to achieve in practice. Carnot Cycle execution. The Carnot cycle consists of 2 isothermal processes and 2 adiabatic processes. During isothermal expansion, the system absorbs heat from the hot reservoir. During adiabatic expansion, the system continues to expand without heat exchange, and its temperature decreases. During isothermal compression, heat is rejected to the cold reservoir. Finally, during adiabatic compression, the system returns to its initial state. Carnot cycle in PV diagram. On the PV diagram, the 2 isothermal processes are shown as curves at constant temperature. The 2 adiabatic processes connect these isothermals without heat exchange. The area enclosed by the cycle represents the net work produced. This diagram helps visualize the relationship between heat and work. It is the classic representation of an ideal heat engine.
Answer B.
In isothermal processes, the temperature remains constant during both heat absorption and rejection. Explanation. A. In adiabatic processes, heat is exchanged during both expansion and compression. This is incorrect because adiabatic processes occur without heat exchange, meaning no heat is added or removed during either expansion or compression. B. In isothermal processes, the temperature remains constant during both heat absorption and rejection. This is the correct answer. In an isothermal process, heat is absorbed at constant temperature during expansion, 1-2, and rejected at constant temperature during compression, 3-4. C. The net work is represented by the area under the heat rejection curve in both processes. This is incorrect because the net work is represented by the enclosed area between the heat input and rejection curves, not just the heat rejection curve. D. Isothermal processes involve expansion and compression without any heat exchange. This is incorrect because heat is exchanged during the expansion and compression in isothermal processes, specifically being absorbed and rejected at constant temperature.
Reversed Carnot cycle in PV diagram. The reversed Carnot cycle represents an ideal refrigerator or heat pump. The direction of the processes is reversed so that work must be supplied to the system. Heat is absorbed from the cold reservoir and rejected to the hot reservoir. The PV diagram has the same shape, but the cycle direction is opposite. This shows that an ideal heat engine and an ideal refrigerator are simply reverses of each other.
Carnot principles. A reversible heat engine is always more efficient than an irreversible one, operating between the same reservoirs. All reversible heat engines operating between the same two temperatures have the same efficiency. Any deviation from reversibility will reduce efficiency. This principle provides an absolute upper limit for all real engines. That is why Carnot is used as the reference standard. First Carnot principle proof. By combining a reversible and an irreversible engine, it can be shown that the irreversible engine cannot be more efficient. If it were, the second law would be violated. This analysis shows that reversibility is the ideal maximum condition. Any source of irreversibility will reduce performance. This is a conceptual proof, not just an assumed statement. Second Carnot principle. All reversible heat engines operating between the same two reservoirs have identical efficiency. This efficiency depends only on the reservoir temperatures, not on the engine design. This means no clever engineering can surpass the Carnot limit. This principle is very powerful because it separates performance from mechanism details. Temperature becomes the only determining factor. Check your understanding number 9. This question reinforces that the efficiency of a reversible engine depends only on the reservoir temperatures. No other factors matter in the ideal limit. This is the core of the second Carnot principle. If this concept is understood, the maximum possible efficiency can be immediately estimated. This also becomes the basis for the thermodynamic temperature scale. Thermodynamic temperature scale. The thermodynamic temperature scale is derived from the relationship between reversible heat engines and heat transfer. This scale does not depend on the properties of any particular substance. The ratio of heat transfers depends only on the reservoir temperatures. In this way, temperature is defined in a universal and absolute manner. This is the basis of the Kelvin scale used in thermodynamics. Reversible heat cycle. In a reversible cycle, the ratio of heat transferred is proportional to the ratio of absolute temperatures. Heat is absorbed from the hot reservoir, and part of it is rejected to the cold reservoir. The difference becomes the net work produced by the cycle. All these relations apply only to reversible processes. That is why reversible processes become the ideal reference. Thermodynamic temp measurement. The Kelvin scale is defined using the triple point of water as a reference. Its value is set at 273.16 K by convention. A Carnot engine is used as a conceptual tool to measure heat ratios. In this way, temperature no longer depends on the properties of a particular thermometer. The measurement becomes fundamental and universal.
Carnot heat engine efficiency. The Carnot engine has the maximum possible efficiency achievable between two temperature reservoirs. No real engine can surpass this efficiency. The efficiency depends only on the hot and cold reservoir temperatures. The Carnot engine becomes the benchmark for all heat engines. All efficiency improvements are always limited by this value.
Answer B. The Carnot engine's efficiency depends on the temperatures of the high and low reservoirs. Explanation. A. The Carnot engine achieves maximum efficiency, regardless of the temperatures of the reservoirs. This is incorrect because the efficiency of the Carnot engine is directly related to the temperatures of the two reservoirs. A higher temperature difference leads to higher efficiency. B. The Carnot engine's efficiency depends on the temperatures of the high and low reservoirs. This is the correct answer. The efficiency of a Carnot engine is determined by the temperature difference between the hot and cold reservoirs. C. The Carnot engine operates with the same efficiency as practical heat engines in real-world conditions. This is incorrect because practical engines are less efficient than the Carnot engine due to real-world losses and irreversibilities. D. The Carnot engine's efficiency is independent of the temperature difference between the reservoirs. This is incorrect because the Carnot engine's efficiency is directly dependent on the temperature difference between the hot and cold reservoirs.
Heat engine efficiency. A reversible engine sets the maximum possible efficiency limit. An irreversible engine always has lower efficiency due to losses. No engine can exceed the reversible limit. If it did, the second law would be violated. This once again reinforces the role of the second law as a fundamental limiter.
Heat conversion efficiency increases when the source temperature becomes higher. If the source temperature approaches the sink temperature, efficiency drops drastically. This explains why high-temperature power plants are more efficient. Temperature difference is the main factor determining performance. All of this is still limited by the Carnot principle.
Thermal energy quality. High-temperature thermal energy has better quality for conversion into work. Low-temperature energy is difficult to utilize for producing work. This shows that not all energy has the same usefulness. This concept is often called energy quality. The second law explains this quality difference at a fundamental level.
Coefficient of performance, COP comparison. A reversible refrigerator always has a higher COP than an irreversible one. No real system can exceed the reversible COP. The COP value is strongly influenced by the temperature difference between the two reservoirs. The smaller the difference, the larger the COP. This again shows the important role of irreversibility in reducing performance.
Check your understanding, number 11. This question reinforces that the reversible COP is the maximum limit that cannot be exceeded. All real systems must be below this limit. This is a direct analogy to the Carnot limit for heat engines. If this concept is understood, expectations about system performance become realistic. The second law, once again, acts as the main guideline.
References. The references show that all of this material comes from internationally recognized standard thermodynamics textbooks. The main reference is the book by Çengel, Bowles, and Kanoglu. This ensures that the lecture content is consistent with global teaching practice. Students can use this book as the main reference for deeper study. Reference consistency is also important for standardizing understanding.